Okay. In this video today, we're going to be looking at exponential function applications. So how do we actually apply exponential functions to the real world? Like, how do they sort of exist? How do they sort of work? And so in general, the formula, the sort of the shape, the template, what am I read? The form of how these exponential functions look is that one I've just squared up in red there, where a is equal to a naught times e to the kt, where a is some amount. It might be the population of something, it might be the temperature of something, or the weight of something. It's the amount of something and how it sort of increases exponentially or decays exponentially, which we'll look at in a second. A naught is the initial amount. So when t is equal to 0 at time 0, what does it start off at? Does the temperature start off at 25 degrees, or does the population start off at 3.5 million? Whatever it is, what's the initial amount? T is time, and the question will tell you whether that time is in seconds, minutes, hours, years, whatever they might say. And K is just some constant, so some number. Now, if that number is greater than 0, so if that K is greater than 0, let's have a think about what might happen. If K is greater than 0, then what's going to happen is that it's going to exponentially increase. So you're going to get a positive, if you think about it, there's no reflections or anything with the graph of e to the power of something. And so what you're going to get is you're going to get positive growth. And so if k is greater than 0, you're going to get growth. And what the graph will look like is like that. Okay, so the graph will increase exponentially, and that point there, that is your A naught right there, that dot there. So that's where the population starts, if you like. So right there is where, the population starts. It's at, let's say, 3.5 million or something, and then it grows from there. It gets bigger and bigger and bigger. So usually these questions will have, like, say that it's only for t greater than 0, and so you only sort of consider, that part of the graph there, not that part there. If the question says t greater than 0, which most of them will. Okay, so that's what happens if k is greater than 0, we get growth. How about if we get k less than 0? So if k is negative, you'll see that what that does is that gives us a reflection in the y-axis. And so what actually looks like is the following. So you get a graph that looks like this, going like that. Okay, so that's sort of, we've flipped that from here to here because there's been a transformation, reflection in the y-axis. So we get that. And again, you've got this point here. That's your A naught there. That's your initial amount. Let's say it's the temperature of we're about to do a temperature of a cup of coffee, and it starts at 50 degrees, and then it gets lower and lower, and the temperature goes down as the cup of coffee sort of sits on your desk while you're doing your homework. Hope that sort of makes sense. So if k is less than 0, then we get decay. Okay, so decay means something that's getting smaller and smaller over time. Hope that makes sense. So there's our formula. So let's just go to do an example today. So let's have a look at this guy here. So the temperature of a cup of coffee, we just talked about this, follows the model. T is equal to 55 e to the negative 0.03 T. So capital T is the temperature in degrees Celsius, and little t is the time in minutes, as defined in the question there. Okay, so what we have to do in this question, find the temperature up to 10 minutes. Then we have to find when does the temperature drop below 20 degrees. And then finally, we need to find the rate of change of temperature when T is equal to 5. Okay, so let's have a look at this. You do get questions where you have T's and T's, so you've got temperature and time there, so it gets a little bit confusing, but you have to get used to it because you're going to have DT, DT, and that sort of thing, but it'll make sense if you just make sure you concentrate on the capital T is the temperature, little t is the time. So let's have a look at this. Just before we sort of start, remember what we said up here. We said that A naught is the initial amount, okay? So if we look at this question here, that 55 there is the initial amount. That's where it starts off. If you think about it, if we put 0 into here, if we put 0 into there, you're going to get e to the power of 0. So that's all just going to equal 1. So the initial temperature is going to be 55. That's where it starts off. So this cup of coffee, we make this cup of coffee, we plonk it down on a table, and it sits there and it gets colder and colder over time. And we know it's going to decay because of this negative there. That negative will mean that it decays. It's going down. And so it starts at 55 degrees. Unfortunately, there's nothing in this question that asks us about the initial temperature. But that gives us that what this is going to look like, it's going to start off at 55 and it's going to cool down like that. It's going to get lower and lower. Okay, so that just gives us a mental picture of what's happening in this question. So let's have a look at part A here. So A, find the temperature after t minutes. So what we're saying is that little t, the temperature, is equal to 10. And so it's asking us what is big T equal to, okay? So we want to know what the temperature is. Okay, so we'll just plug it into our formula. Nice and easy. T is equal to 55 e to the negative 0.03 times 10. Okay, and so we'll go to that. Definitely don't do these sorts of questions by hand because I don't know what e to the power of negative 0.3 is equal to. So let's just go straight to our calculator. So I'm just going to have to remember that. I hope flicking between screens. So we want 55 times e to the power, and I'm just going to flick back because I've forgotten what it was. That's what happens with me, bad memory. Negative 0.3 times 10. Negative 0.03 times 10. Negative 0.03 times 10. And we'll put that, and it gives us our answer as 40.74. The question didn't ask to round it off to anything, so I'm just going to put it as, I'll just do 2 decimal places. The question will always tell you how many decimal places you should do it to. So here we go, 40.75. So that'll be 40.75. We need to put our temperature is measured in degrees Celsius. So that's my answer is 40.75. Nice and easy, onwards and upwards. So that sort of makes sense. So it started off at 55 degrees. After 10 minutes, it's dropped to 40 degrees. Okay, so the cup of coffee is getting cold. Right. Part B, when does the temperature drop below 20 degrees? So we want to find out when T is equal to 20. So, oh, no, I don't want to do that. I want to find out where capital T, so where the temperature is equal to 20 degrees. We want to know when that is. And so we want to know the time that happens. Okay, so put that into our formula. So we get 20 is equal to, I'm just going to go back up to my formula, is equal to 55 e to the negative 0.03 t. And we want to solve this for t. So solving this for t, I'm just going to go straight to CAS because, again, these questions you'll always have CAS calculator because there's sorts of things that you can't do logs of these sorts of numbers. They're awful. And so we go straight to that. So I'm just going to go and solve. I should do a split screen, really, shouldn't I? Let's do that. Maybe I can't do it while I'm recording. That didn't work. Here we go. So 20 equals 55. So we go solve. 20 equals 55 e to the power of negative 0.03 t, I believe it was. I'm just going to double check that I got that all correct. Negative 0.3 t. Yes, that's what we want. And we're going to be solving this for t. Okay, and it says that time is equal to 33.72. 33.72. Okay, and what was T measured in? T was measured in minutes. Okay, so what that's saying is that after 33.72 minutes, the temperature is going to drop below 20 degrees. So that's the answer for part B. Last question, let's have a look at C. And what C is, find the rate of change of temperature when T is equal to 5. So when something asks for the rate of change of temperature, what it wants is the derivative. So this is when we need to bring calculus in. And so what it wants the change in temperature with respect to time. So dt, dt. So d capital T, d small t. Okay, the rate of change of temperature with respect to time. Okay, so let's find the derivative dt, dt. So firstly, so remember when we're differentiating e to the power of something, it stays the same as e to the power of something, but we need to multiply it by the derivative of that something. Okay, so dt to d, I'm having to flip between two things there, 55 e to the negative 0.03. I should remember this by now. So it's going to be 55 e to the negative 0.03 t. It's going to be that, but then we need to multiply by the derivative of that inside function. So the bit that's up the top here, we need to multiply by the derivative of that. What is the derivative with respect to t of negative 0.03? That'll be negative 0.03. Okay, so that'll be the derivative there, and we'll just clean that up a little bit. And we could do this all on CAS calculator. That would be fine, but I just wanted to make sure to remind you about how to do that. So 55 times 0.03, that's 300th, 165. It's going to be 1.65 something. Anyway, I'll go do it on CAS. 55 times 0.03. Okay, so 1.65. 1.65, so that'll be negative 1.65 e to the power negative 0.03 t. And we want the rate of change when t is equal to 5. So we want to have a look at this. So what we want, therefore, dt when t is equal to 5 is equal to negative 1.65. We're just subbing in t is equal to 5 here. E to the negative 0.03 times 5. Okay, so we'll go do that. It was negative 1.65. Oops, why did I do that? Because I didn't do subtract. Negative, what was it? 1.65 e to the power negative 0.03 times by 5, and we get negative 1.42. Okay, so negative 1.42. Just remember that. Negative 1.42. Got the negative. Okay, and what are the units here? So this is dt. That's how much the temperature changes over time. And so what is the degree? So the units of temperature is degrees Celsius per, and the time is t was what was it? Time in minutes. So that's minutes. Okay, so make sure you put your units in there. So let's just have a think about what this means. The rate of change of temperature when after 5 minutes is equal to negative 1.42 degrees Celsius per minute. What that means, and you really need to understand what that means, is that every minute the temperature of the cup of coffee is dropping by 1.42 degrees. Okay, so hopefully that sort of makes sense. Every minute, oh, I was trying to draw something, but it did something funky. So it means it starts off at 55, and every minute it drops by 1.42 after every minute and another. So that's what's happening here. And sorry, it doesn't mean every minute it's dropping by 1.42. It means at exactly t is equal to 5. So at this point here, at that point there, at that exact moment, then the rate of change, it's dropping by 1.42 at that exact time. Okay, that's probably a bit of a better explanation. Hope that makes sense. We'll see you in the next video.